Previously, we learnt about quantifiers and logical connectives. These are the instruments that we have in the mathematical language that enable us to write expressions about different objects that have precise meanings. That is, when given any mathematical expression, I know exactly what it means. Or in other words, there can only be one meaning whenever I read out the mathematical expression that I have. For all can mean for all, for every, and for each, which means whenever this symbol is used, we have something like this. If we say for all x, ax, we mean that for every x, this is true. For each x that we choose, this is true, right? For all x that exists in whatever the set that we're getting x from, ax is true, right? There exists, on the other hand, is that if we write there exists y, we are saying that there is a particular y that exists for this to be true, which means there is a y or there exists a y. So whenever you see those words in a mathematical expression or in a mathematical statement, you can replace those words with this symbol. And so same for the for all, which means for every and for each. Good. Now we'll move on to some examples. X is an element of real numbers. That is. Then I write a statement that says what does this statement mean? What exactly am I saying? Now, I'm saying that for all x that I can choose, which means for any x that is an element of the real numbers, right? For all the x values that exist, this should hold, right? But now, when you think about this, x squared plus 1, if we choose any value of x that we want, for example, we choose x is equal to 1. 1 is a real number, but 1 squared plus 1 is not equal to 0. Which means, already I can see that we use the wrong quantifier here. This statement can be true for a particular thing. This statement can never be true actually for any real number. Why? Because x squared is always a positive number. If you add two positive numbers, they'll never equal 0. Which means for any x that I can think of that is an element of reals, this statement will never be true. Suppose we had written there exists an x such that x squared plus 1 is equal to 0. This could also never happen, even if we choose x to be 0. 0 plus 1 will never equal 0. Right? Which means this statement is false in general. This is false. This also is false. For the next example, we're going to assume that x and y are both elements of the reals. Right? Now, I write down a statement that says there exists a y for all x, x plus y, right? There is a specific y, right, that should satisfy this statement for whatever x that I choose. Is that true in general? Let's think about this. If I choose whatever x that I choose, what do I need y to be for this to be true? Y has to be equal to minus x. But is there a universal y that satisfies this? The next example says, for all x, there exists a y for all z, such that x minus y z plus z. So this is saying, for any x that I choose, there exists a y for all z, such that this holds. I'll say that slowly. For any x that I can choose, which is this part, right, there is a specific y for any z, such that this will hold. Let's think about that. Well, this here is this. Right? Which means if I choose any x, there should be a particular z that for whatever z value that I have, this will hold. Right? Now, I choose x to be 2. Right? And I'll choose z to be 5. There should be a y that satisfies that. But suppose I choose the same 2, I choose 6 there. I still want that to hold. Which means we are saying that there is a specific y that exists such that for any z that I choose, this statement should hold. And already we can see that from this example that we have here, that can never be true. So now, let's look at these two expressions, right? The first expression says that for all x, there exists a y such that y is equal to x squared. Which means what this is telling us is, for every x, there is a specific y that is such that y is equal to x squared, right? In other words, we are saying that every x has a square, right? Let's move to the next statement. This next statement says there exists a y such that for all x, y is equal to x squared. In other words, it's saying that there is a universal y, right? Such that whatever x that I pick, this should be true. And obviously that is false. And can you see that we just swapped the order of these two quantifiers, and immediately the meaning of the expression was different. So we can get to see that it matters the order that we write these quantifiers and the symbols that we attach to them. The order is important. So with the examples that we looked at today, we have learned that quantifiers place very precise and exact meanings on whatever mathematical expressions that we might want to build. Which means no matter where any person is, where they are, when they look at your work, when they read whatever expressions that you have put down, there's only one way for them to be able to interpret it, which is some of the things that we love about mathematics. The mathematical language is very precise. There's no confusion, there's no ambiguity of any sort. Everything has one exact meaning.